I want to show you now where these substitutions are coming from. So far, we've only done the first type that you see at the top of this screen. But the idea here is that we have a couple of trig identities that are just going to be very useful, and those trig identities are of this form. Um, we know that cosine squared is equal to 1 minus sine squared of x, and we also know that secant squared x is equal to 1 plus tan squared x, and sort of equivalently, we know that tan squared x is equal to secant squared x minus 1. So the idea is that we're trying to get the expression underneath the square root sign to look something like these expressions so that we can turn a more complicated expression under the square root sign into a simpler square. If you think about it, what happens is if I can make the expression under the square root sign look like 1 minus sine squared x, then I can simply change it to the square root of cosine squared x, which, and I realize some of you are astute and you notice that I omitted the plus and minus, which I'm going to do for these types of problems, but at least up to a plus and minus, the square root of cosine squared x is equal to cosine x. So this is the operation I'm trying to leverage here. So the rules that come from that are if we start with an integrand of the form a squared minus b squared x squared, then use the substitution x equals a over b sine theta. And if you look at the second one, if we have a, and keep in mind a and b are just constants, x is the only variable here. So if I have a squared, square root of a squared plus b squared x squared, then I want to use the substitution x equals a over b tan theta. Now why? Because if you look at this, what we have here is we have a constant plus some other constant times x squared. Well, that's kind of what we have here in the second line. What we have secant squared is equal to 1 plus tan squared x. So what we have is the constant 1, and we have then a function of x squared on the on the right. And similarly in the last one, we've got b squared x squared minus a squared, and that's kind of what you see in this third line. You see secant squared x, so you have the expression involving x, and then minus a constant. Let me just show you with regard to the second line here, a different color. With regard to the second line here, let me just show you how this works if you were to use the substitution x equals a over b tan theta. What you would get is you'd get square root of a squared plus b squared x squared. If I let x be a over b tan theta, that's going to be the square root of a squared plus b squared times, I'm going to square this x here, so that's going to be b squared times a squared over b squared tan squared theta. Now let's simplify that a little bit more. These b squareds are going to cancel, giving me a squared plus a squared tan squared theta. And I can now pull out a factor of a squared, so that's going to be the square root of a squared times the square root of 1 plus tan squared theta, and that just equals a square root of 1 plus tan squared theta, which equals a square root of secant squared theta, which equals a secant theta. So the point is that by using that substitution, what I end up with is just some constant times times secant theta, which is more likely to appear in an integral that I can actually evaluate. So that's the reason that this works. We're just trying to get this expression, or an expression like this, one of these three expressions, to appear under the square root sign by making an appropriate substitution. So with that said, the rule that you want to follow is if you see constant minus b squared x squared, then you use a sign type of substitution. If you see constant plus b squared x squared, then you use a tangent type substitution, and if you see b squared x squared minus the constant, then you use a secant type substitution. So we'll do examples of those in future examples.